Good evening, everyone. Happy National Mathematics Day to all. This day was declared as National Mathematics Day by our former Prime Minister Dr. Manmohan Singh in 2011 to celebrate the birth anniversary of Srinivasa Ramanujan, one of the greatest Indian mathematicians. We have gathered here today to commemorate the 135th birth anniversary of this legendary mathematician. With almost no formal training in mathematics, he made pioneering contributions to number theory, mathematical analysis, infinite series, and continued fractions. He became one of the youngest fellows of the Royal Society and the first Indian to be elected as a fellow of Trinity College, Cambridge. His mentor and collaborator, the great English mathematician G.H. Hardy, has said the following about Ramanujan. Suppose that we rate mathematicians on the basis of pure talent on a scale from 0 to 100. Hardy gave himself a score of 25, J.E. Littlewood 30, David Hilbert 80, and Ramanujan 100. To talk about his life and work, we today have Surya Teja Gavva uh, from Rutgers University, USA. He completed his undergraduation from IIT Bombay. His primary research interest is in analytic number theory and related topics such as L function, automorphic forms, and spectral theory. So I request Surya to start now.
Yes, thank you for the introduction. So let's start. So it's a pleasure to talk about Ramanujan. Like his life is fascinating. His mathematics is so beautiful. Yeah. So let's start. Yeah. So this is Ramanujan. The picture of Ramanujan, the man who knew infinity. Literally. So this is a book on Ramanujan by Robert Knighel called "Man Who Knew Infinity." It's about his life. His biography. It's a very well written book. So if you haven't read it, please go and read it. So yeah, so let's start. So Ramanujan is born on December 22nd, like 135 years back in 1887 in this place called Pallipalayam, Erode in Tamil Nadu. And he grew up in this place called Kumbakonam. Okay, so his parents were Komala Tamil and Kuppuswamy Srinivasa Iyengar. So this is Komala Tamil here, the first picture, and these are the places. So this is a place he was born at, and this was a place he lived in Kumbakonam. Okay, so his childhood, he had a really religious upbringing, very Hindu traditional upbringing. He spent hours in a temple lobby listening to drums, doing mathematics. He believed that his discoveries came to him as visions from this goddess Namagiri, is a local goddess, this is town goddess. And there's a statement by him which expresses his religious feelings and how it inspired him to do mathematics. An equation for me has no meaning unless it expresses a thought of God. Okay, so let's see. So we'll start. It's one of the first schooling he has been. Like first schools he studied, he joined in is a school in Kumbakonam called Kangayam Primary School. So there's a story like that his friends C.V. Rajgopalachari recounts. There was a arithmetic class when some teacher was explaining arithmetic and how to divide numbers. If you have 3 bananas and if you divide among 3 students, each student gets 1 banana each. Similarly, if you have some 10 bananas and you divide among 10 students, each of them still gets 1 banana each. And Ramanujan just like stands up and asks, so if no banana is distributed to no student, how will everyone still get a banana each? So he was, you can recognize that he's asking what is the value of 0 over 0. So this already, like this is in primary school almost. So this story already tells you that he was like his creativity and imagination and somehow his fascination with infinity, right? Like somehow he was always fascinated with this idea of infinity and limits, and yeah. So this was this was in primary school, and then I joined Kumbakonam High School, and he was an outstanding student. He won many academic awards. He won scholarships. He did mathematics on his own. He started writing down his results in some notebooks. He would first write compute stuff on a slate. This was a slate that Ramanujan used. This was the American mathematician Bruce Berndt holding Ramanujan's slate. He would write down these results on the slate, work out results, and then note them down in his notebooks. Okay, so, and this is his Kumbakonam High School. Okay, so a story at Kumbakonam High School. Apparently at some point, a senior in the school comes and asks Ramanujan, oh, the following problem: square root of x plus y is 7, and x plus square root y is 11. Then what are the values of x and y? So Ramanujan was like much younger. Like these are seniors in high school, and Ramanujan was like much younger. But he immediately responds that x equals 9 and y equals 4. So yeah, you can check that. You can, for instance, you can just plug in x equals 9 and y equals 4 and check that these are the solutions. But for those of you who are interested, in general, you can solve it. So if you actually eliminate variables and solve it, you get a 4th degree equation in x, degree 4 equation in x, but only x equals 9 is the solution that makes sense because you have all these square roots. Is that clear? Like you just eliminate, you have these two equations and you eliminate, and you get a 4th degree equation in x. For instance, like you can write y equals 7 minus square root x, and x plus square root 7 minus square root x is 11. And that will give you some equations like 7 minus square root x is 11 minus x whole squared. And that will further give you x equals 7 minus 11 minus x squared whole squared. So this is a 4th degree equation. But x equals 9 is the only real, I mean, there are a lot of real solutions, but the only solution that corresponds to a solution to the equations that we started with. Okay, so yeah, so this is some, these are some stories from Ramanujan's high school. Like he showed exceptional ability in his, even when he's quite young. Okay, so then like while he was getting into high school and so on, he really started some of the books that influenced him were this book, a classic book by Loney called Plane Trigonometry. It is a book on trigonometry, and it has different trigonometric identities and so on. So he mastered this book, and he discovered a lot of identities on his own, and later some, like, only to his disappointment that they're already known. So he already was he's a master at manipulating these identities, trigonometric identities, and so on. Yeah. So another book that during the high school he would go and get it from some college libraries around, and some other friends who were studying in college. This book called Carr's Synopsis, a synopsis of the elementary results. It's a book on pure mathematics. It has 4865 formulae, all of them without proofs, just a lot of formulae in different areas of mathematics: algebra, trigonometry, geometry, and calculus. And 2 biographers of Ramanujan and his friends, Sheshu Iyer and Ramchandra Rao, say that this was this book which awakened his genius. He set himself to establish the formulae given therein. As he was without aid of other books, each solution was a piece of research. So far as he's concerned. So he would take this, so he had all these formulae, and he tries to derive those formulas and get, and then in the process, he discovered a lot of new identities, a lot of new mathematics. So it was this book that really like started inspiring and like it's really the point where Ramanujan got introduced to all this infinite series and Fourier series, continued fractions, and so on. So for instance, there are these elementary identities, so these are some sample of identities from the book. So you guys, it is available online if you should check it out. So like for people who are interested in analysis, or even like, I think like the identities are fascinating. For instance, even the very simplest, this is the very elementary identity, like the first identity, but it just, to look at it is so beautiful, and it shows up in like more advanced settings, in the sense that this identity belongs to Galois theory and like theory of solving equations and radicals and so on. And some other like identities. For instance, there's this integral, it's called a Fulani integral. He uses, so this shows up in the book, and Ramanujan uses its integral to compute. So it's easy to, yeah, for those of you if you don't know how to prove it, it should, like, yeah, it just a switch of okay, you should, it's an exercise. You should write it. Just introduce an extra integral inside and then switch the integrals. And there's this integral which belongs to the hypergeometric an expansion, which is an hypergeometric series expansion. Okay, so there are all these fascinating and beautiful identities that he would play with and like discover much more, right? So this was still when he was in high school. Okay, so then he passed his matriculation in 1904, and he joined this government art college in Kumbakonam. But he got preoccupied with mathematics and he neglected everything else. And because of that, he flunked. He was attempting this examination called FA at that point, and he flunked this examination. And then he went and joined, a year later, he went and joined this college in Madras, Pachiyappa's college. Even there, it was the same problem. He was not, he was doing really well in math, but he flunked because he didn't want to, like he didn't care about other subjects like English and so on. Okay, so after he dropped out of college, so it's really it's time when his struggling years started. He was married to Janaki, who was 90 years old at the time, 1908, and then he had to really find a job to help his family because he was to get out of poverty. And so he found a job as a clerk, and but still he was working on mathematics all the free available time. So it was those years which were tough for Ramanujan, but still he was working on mathematics actively, and he would produce a lot of mathematics. He would write them down in his notebooks, and he showed somehow he got in contact with some Indian mathematicians, like mathematicians who were in India at the time, like British. So India was British colonial rule. So yeah, so there were different mathematicians from some English mathematicians and like local Indian mathematicians. So he got in contact with these mathematicians. Some of them were Ramaswamy Iyer, Sheshu Iyer, Ramanujan, Ramchandra Rao, and Professor Griffith. So all these people he got in contact with, and he would somehow they look at his mathematics and like they were really mind blown. Like it's just something that they have never seen. His expertise in manipulating these series, for instance, continuum fractions, this hypergeometric series, some of this stuff is something that none of these people have ever seen. It's of the highest quality that they couldn't even imagine what can the nature of, like they didn't even comprehend the depth of these mathematics. So but they knew that they could recognize his genius, and they tried to they helped Ramanujan to kind of Ramanujan was given some funding, and like they helped him to get in contact with the British mathematicians and even publish some of his work in Indian mathematical journals. So at this point, for instance, these are some statements by these biographers. So for instance, Sheshu Iyer says that Ramanujan's methods, like they would try to, like these people would try to make sense of Ramanujan's mathematics, but it was really terse. He doesn't like giving long explanations. It was really terse, but like it was like really beautiful identities that he comes up with. So Sheshu Iyer says that, okay, it's so terse that it's hard for like a normal reader to follow such intellectual gymnastics. And also Ramchandra Rao talks about the state in which Ramanujan was at the time. He came to, he was in Madras. He was trying to somehow, so all he wanted really was, he was in dire poverty, and he really wanted to have some leisure so that he can work on mathematics. All he wanted was some food and food for survival. If he can have some basic resources, some allowance, so that he can focus on mathematics. So, but somehow, like University of Madras and people give him these. He gets some scholarships, and he starts working and publishing on some mathematical results. So one of the first papers that he publishes is this paper called Some Properties of Bernoulli Numbers. Okay, so I don't know, do you guys know what Bernoulli numbers are? So it just so imagine that you are writing down formulae for summing numbers, 1 plus 2 plus 3 plus so on, and it is some polynomial. Similarly, if you try to write a formula for 1 squared plus 2 squared so on n squared, there is another polynomial. So you can similarly keep doing it for any sums of cubes, in general sums of powers of numbers. So and that will be a polynomial. So you'll see that the polynomial will have some coefficients. There are some binomial coefficients, but if you forget about apart from the binomial coefficients, there are these other numbers, explicit numbers. So these numbers are called Bernoulli numbers. So just try to write down an expression for the polynomial corresponding to summing the powers, and the numbers that you see there are called these Bernoulli numbers. So for instance, the first few numbers turn out to be 1, -1/2, 1/6, 0, -130, and so on. Okay, so these are such basic. These numbers were first observed by Bernoulli and so on, but these are such basic numbers. They are rational numbers, and people. Yeah, so for instance, let's see, they show up everywhere in mathematics. For instance, whenever you want to sum over integers, something like discrete integrals, or you want to compute some things like values of zeta, which are also some sums over integers, and in general, some formulae called Euler-Maclaurin. So in all these places, these numbers show up because, yeah, so even in some basic sums over integers, these show up in general more, even if you take some more complicated sums over integers, like these numbers show up. And there's a way to generate these numbers. It's by this infinite series. Like if you, so you write down this infinite series, and the infinite series will help you to, so by expanding x over e to the x minus 1, you can compute these Bernoulli numbers. Okay, so they have really many interesting arithmetic properties, so I should go and check it out. But the point is, Ramanujan computed with hands. These numbers are like they grow very fast. Then there are some. So Bn is some, let's say, some rational number. So these numbers grow really fast, and he computed like tons and tons of Bernoulli numbers by hand, and he also computed some properties of these. So it's a rational number. You have to number over a number. So you computed some arithmetic properties like what primes divide the numerator, what primes divide the denominator, and so on. So this is one of his first papers. Okay. Yeah. So if you have any questions, you can stop. Like I guess we'll take enough time to finish. So yeah. So you can stop and ask me. It's fine. So yeah. So that's Bernoulli numbers, and then it's one of his first papers, and then he started posing some questions in this Indian mathematical journals. For instance, there's this question that he poses: square root of 1 plus 2 times square root of 1 plus 3 times square root of 1 plus 4 times, so on. So this is infinite expression that he writes, and he wants people to compute. So he's just asking, what is this value? So can anyone guess what this value is? This people look at this and it's they're just mind blown. How do you even like treat something like this? Okay, so let me I guess fine. So let me tell you. So the answer is 3. So the way you do it is let's see. So way the Ramanujan does it. So it's just 3 is just 1 times 3, and 1 times 3 is 1 times 3 is square root of 9, so it's 1 plus 8, and this is 1 times 8 is 2 times 4, so which is 1 plus square root of 1 plus 2 times 4 is 60. Square root of, sorry, so 1 plus 2 times, okay, so 2 times 4 is 8, so 4 is square root of 16, so it's 1 plus 15, and you keep doing it. So 1 plus square root of 1 plus 2 times 1 plus 3 times 5, yeah, so you can see that you can keep writing down this expression, and you'll see that Ramanujan says, so you keep doing it, and hence the number is actually equal to 3. Yeah, so any questions on this? It just start with 3 and you keep repeating this process. So essentially he's using this identity, n times n plus 1 can be written as n times 1 plus n plus 1 times n plus 3. So if you use this identity, you can keep doing it, and that's his proof for why 3 equals this expression. So I mean, ideally you should be careful like when you deal with these infinite expressions, but he knows that this is right. I mean, if you even if you compute some few values of the truncation of the series, you can see that it's actually converging to 3, and you can actually prove that it's actually going to 3. But okay, so yeah, so he had this like magical identities. And he somehow really loved dealing with infinite expressions. That's why he really is man who knew infinity. It just and it started all the mathematicians in the Indian circles. Okay, so so that's one thing. And then he was studying some equation called x squared. This right now this is called Ramanujan-Nagel equation. So this equation is x squared plus 7 equals 2 to the n. So this Diophantine equations, he was studying this, and he said that there are only a few solutions, basically the 5 solutions corresponding to x equals these numbers, and n equals these corresponding numbers. Okay, so this was what he conjectured, but it was proved later by Nagel. So for those of you who want to understand how this proof goes, I have a few lines. It's just that you work in this ring of, who know some algebraic number theory, you work in this ring of integers of q square root -7. So what does that mean? So you have x squared plus 7. X squared plus 7 can be written as x plus square root of -7 times x minus square root of -7, and this equals 2 to the n, right? Somehow, so we have this initial equation which had some additions and multiplications. Somehow, if you have both additions and multiplications in general number theory, it's hard to deal with equations where there's both additive and multiplicative stuff going on. But somehow, when you write x squared plus 7 as this product, now thinks there are two stuff that you're multiplying and equals 2 to the n. So now somehow, if you understand some primes in this ring and so on, like basically if you understand numbers of the forms x squared plus 7y squared, but like in the classical language, it's really about understanding numbers of the form x squared plus 7y squared, then you can say that you can solve this equation explicitly. Okay, so for those of you who know what I'm talking about, this is the starting point, and once you know this, it's a few steps to show that these are the only solutions. Any questions? Okay, so let's see. So this is all the stuff that he was doing while still was in India, like he was like publishing stuff. So people recognize this that he's genius, and so Indian mathematicians started sending some of Ramanujan's work to places in London and so on. So, and a mathematician at University of London, Professor Hill. So he says that, he looks at Ramanujan's mathematics, some of his notes and so on, and he says, yeah, Ramanujan is definitely a man of taste, and it's and some ability, but he has written some equations, some crazy equations like this: 1 plus 2 plus 3 is -1/12. 1 squared plus 2 squared plus 3 squared is 0. 1 cube plus 2 cube plus 3 cube, so on. Infinity is 1/120. So you wrote down some crazy equation like this, which are obviously false. You can't just, these are divergent series. If you add all those numbers, you would not get a number which is -1/4. So that was a response from one of the first correspondence between Ramanujan's work and English mathematicians. So he couldn't comprehend what this stuff means. It's just so bizarre. You add all the numbers, why do you get -1/12? So, but what Professor Hill didn't realize at that point is that Ramanujan was really talking about some much deeper concept, something called analytic continuation of the zeta function. So you write down, this zeta function is this expression. So summing over integers of 1 over n to the s. For instance, if you plug in s equals 2, you get 1 plus 1 over 2 squared plus 1 over 3 squared, so on, 1 over 4 squared, and so on.
If
So
Ramanujan gave any context of those summations?
Yes. Like so for him, he was manipulating the summations he had written. For instance, for what Ramanujan did was that what I think Ramanujan did, or what we think Ramanujan did, is just that he knew that there are other expressions which are equal to zeta function. For instance, this expression here that we wrote only makes sense for s large, s greater than 1. But then he said he somehow he knows a lot of integrals, a lot of ways to manipulate series, and so on. And so, for instance, you might have realized that zeta has another expression. For instance, you can see that zeta can be also written in terms of this complicated integral stuff. There is some infinite series.
So he was sort of studying the zeta functions.
Yeah. Somehow he's studying zeta function, and like he knows a lot of properties of the zeta functions, and then he can see that when you plug in like things like -1 in this, so it doesn't make sense to plug in -1 in this initial expression that we start with, but you derive another expression which is equal to the same. These are two identical expressions. It's just that this expression doesn't make sense for s greater than 1, but this expression makes sense for every s. Except
but he might not be knowing the analytic continuation and other stuff.
He didn't know. This idea of analytic continuation is not something that he might have known, but like intuitively, even the way you think of analytic continuation is that find another expression that makes sense, which equals the same expression. So for instance, right, so 1 plus x squared, so on, is equal to 1 over 1 minus x. This makes these two are equal quantities when x is less than 1, like small, absolute value of x is less than 1. But this, the left side, this guy doesn't make sense always, right? If you plug in x equals 1 or x equals 2, this doesn't make sense. But this expression makes sense. And that's exactly the way he was dealing with it. So you have an expression, you find another expression which makes sense at the places where the initial expression didn't make sense. And then you plug in values and you see that you get some values like this. If you plug in s equals -1, which kind of corresponds to summing 1 plus. In the formally, it corresponds to, like, if you formally plug in, it's just 1 plus 2 plus 3 plus so on. Right? So, and that turns out to be -1 over 12, and zeta minus 2 is 0, and -3 is 1 over 20. So, yeah, does it make sense? It's just that you found another expression for the zeta function, and you plug in these values, and you can see that you can compute those values. Okay, so so again, you can see that these zeta values are already again related to, if you have seen this before, the values here will be related to the Bernoulli values that you have seen before. So there is some correspondence. Okay, so this is some beautiful stuff that even like some top mathematicians didn't realize, but like people like Hardy knew what was happening. So Hardy is this English mathematician. He was one of the top analysts at the time. It was at Cambridge. So Ramanujan somehow got like he looks at this book. He got hold of this book called Orders of Infinity that Hardy has written, and and Hardy says that there is no formula or no definite expression that is known to compute the number of primes less than some number. Okay, so if you want to given a number, I want to figure out how many primes exist. It's like there's no definite expression known, and this catches Ramanujan's eye, and then he decides to write.
It is prime number theorem, right?
Yes, the prime. So yeah, at that point, So at that point, prime number theory was not completely proved. So
I think gave something, right?
Yeah. So you know that this is like there's an asymptotic like this, but I think it was proved in the beginning of it was also proved in the beginning of 20th century. But yeah. But yeah, we still do. I mean, like just we understand some asymptotics, but like we still don't understand what these things are. There are further terms. For instance, the best understanding of this is equivalent to Riemann hypothesis. So yeah, so this is something Hardy has said in a book, and then that catches Ramanujan's eye, and so he decides to write a letter to Hardy. Right. So this is a letter that he writes to Hardy, and he says that, oh, I beg to introduce myself as a clerk, and I have no university education. But I've trodden through. I haven't trodden the regular course work, but I'm striking out a new path for myself, right? And I'm making investigations of divergent series, and some of the results are termed as startling by the local mathematicians. So he writes this letter, and like in 16th January 1913, and he writes some other, like he also talks about how he studied this function called the gamma function, and how it makes sense for values, just like what we talked about zeta function. It makes sense for values that it's not supposed to make sense. Even this gamma function, he said, I know how to make sense of it at places where it's not really defined in the beginning. So yeah, and then he attaches a lot of formulae in the so he handwritten formulae about a lot of series and like expressions involving continued fractions, hypergeometric series, and trigonometric series, and so he has a lot of expressions that he writes down. For instance, these are some of the formulae that he sends in the book. So there's some hypergeometric kind of series, some definite integrals that he was fascinated with, and again, infinite. There's infinity there, and definite integrals with some infinite products in there, and then these are continued fractions. He computed that there is this continued fraction at some e to the minus 2 pi is related to both e pi and this famous number called phi 1 plus square root phi over 2. Okay, so he sent all these crazy formulae, and Hardy replies back. He looks at all this, and he replies back. Hardy's reaction was that, oh, these formulas completely defeated me. I have never seen anything like this before. It could have been only written by a mathematician of the highest class, right? I mean, they must be true, because not normal people wouldn't have imagination to even write something like that. It's just so. That was what Ramanujan, Hardy was really like impressed by the kind of results he sees in Ramanujan's letter. So yeah, so there are a lot of, so he replies back saying that, oh, there are some results that are already known from the that we have stated. It's just that not in this form that people already know. There are some results that are new, but probably not that important. They might they're interesting for some purposes, but not that important. And there are some results that are really new and important. And they have series of conversations. Ramanujan says, oh, I have found a friend in you who views my labors sympathetically, and he talks about getting some letter from him, and they keep there's some few exchange some letters, and then finally Hardy invites Ramanujan to Cambridge, and they have a very productive collaboration, and they published like 30 papers, groundbreaking papers during that time in Cambridge. Like, for instance, like initially Ramanujan, like because of religious reasons, he doesn't want to step out of India, but like somehow Hardy sends some English mathematicians to like convince Ramanujan. Ramanujan ultimately agrees and goes to Cambridge. Okay, so when Hardy meets Ramanujan, it's just that he's startled that this guy who knows so much, he's a master of dealing with this complicated stuff called modular equations, elliptic functions, something called complex multiplication, and then he was obviously a master of infinite series, continuous fractions. He knew a lot about zeta function, which is quite crazy, but in spite of all this, he didn't really know what a complex variable is. He didn't know basic complex theorems like Cauchy theorem and so on. So it was like, yeah, so the limit. It was like he was really fascinated with Ramanujan, the way Ramanujan's mind works.
This
And
was the perception before the start of collaboration or after?
no, this is after, when he met. Like this guy who knows so much, who can deal with so much stuff, but he doesn't understand what a complex variable is like. So the way he's perceiving these objects is completely like,
Probably he
very
was even
different.
not knowing zeta function as zeta function, but just as some summations, right?
Yeah, as an expressions. Basically, he
Yeah.
never thought of it as like, and just for him, everything is just an expression, and it has beautiful, and he knows how to deal with these beautiful properties. Okay, so and then during his time, it came.
Excuse
Yeah, yeah.
So leading up to this point, were there any formal justifications which Ramanujan provided?
Oh, here, no, I mean, like, yeah, he had trouble, like, he didn't understand what it means to really so this was one of the problems. Hardy and Littlewood were trying to like get him to like write stuff rigorously, and this idea of proofs and so on. But for him, it just like, he could see certain things are true, like maybe because he's computed a lot of stuff, and he knew that I didn't know how it might work, but like it's from his computation, he realized that something is true, and he strongly believed that those things are true. But yeah, it was not in the sense of the traditional proof-based stuff. Like,
And neither perhaps he has any kind of any big theorem in mind to prove, right? He has no big theorem.
Yeah, he was just really
reach our goal. There was
there was no goal like that. He was just, you have these expressions, and he just keeps deriving beautiful consequences using those expressions. Yeah. So then during his time at Cambridge, he also met a lot of other mathematicians. So for instance, like he met Littlewood. Littlewood is one of the world's finest analysts. He was one of my favorite mathematicians. He met Littlewood, and Littlewood says that he would try to teach Ramanujan about some standard, like so-called standard rigorous mathematics, but it was impossible for him, because when he starts speaking to trying to teach Ramanujan would come up with like original ideas, so many original ideas. He would just shoot like beautiful ideas that it's hard for Ramanujan to just Littlewood to persist and ask him to focus on rigor or like standard methods of proving things and so on. So he decided to let Ramanujan free. But yeah, Ramanujan manages to learn this, some Hardy and Ramanujan wrote some really, really impressive papers. So we'll see about that, which are in very modern, fit modern mathematics. It's not just that everything is in the style of Ramanujan. So then in Cambridge, he also met other mathematicians. This mathematician called Barnes, who was the mentor of Ramanujan. And then he met Mahalanobis, who was a student at Cambridge at that time. Mahalanobis is the founder of Indian Statistical Institute. He was one of the great statisticians. So, and there are very interesting stories that happen between Mahalanobis and Ramanujan. If you see, yeah. So these are some pictures from the time of Ramanujan at Cambridge. While he was getting his degree. It was at that time called Bachelor's for Research or something. It's later called the PhD, but yeah. So this is fine. So he's Cambridge. He's doing mathematics is really good, and like he's really collaborative. Stuff is happening at the time, but at the same time, there were a lot of hardships that Ramanujan has to go through. There was rampant racism, and then there was World War I, and a lot of professors at Cambridge were drafted into the war. And then he was a vegetarian, and he couldn't get access to vegetarian food. In general, like vegetarian food is not a thing in London at the time. Also, because of the World War, it was hard to get access to vegetarian food, and there was malnutrition, and because of that, there were several health issues. But despite all these health issues, he did groundbreaking work, and that kind of got him elected to the Fellow of Royal Society. Okay, so now we'll discuss some of his mathematics that he's produced during his time at Cambridge. So let's see. One of his first papers is something called highly composite numbers. So a number is called highly composite if it has more divisors than the numbers which are smaller than it. So a number is called highly composite, and is called highly composite if the divisors, you compute the number of divisors of a number, and it has more divisors than numbers smaller than it. For instance, you can imagine writing down the divisor sequence. Just write down the divisors of 1, divisors of 2, the number divisors 1, 2, 3, 4, 5, and so on. You keep listing down number of divisors of these numbers, and you see that at some point you have these maximas that occur. So 2 is bigger than everything before, 3 is bigger than everything before, 4 is bigger than everything before, 6 is bigger than everything before. Then 8, this 8 is bigger than everything before, and 9 here, and so on. So, and the corresponding numbers are 2, 4, 6, 12, and so on. So these are the numbers for which the divisors that they have are the biggest among, like you have the most number of divisors compared to everything before. Okay, so these are some kind of quantities that, so there's a pattern in the divisor sequence that Ramanujan observed, and these are those numbers. And Ramanujan was interested in asking this question: so how many of these numbers exist? How fast? How far? Like how many such numbers exist below some given threshold? Like less than some number x. How many such numbers exist? You write down these numbers and want to know how many of such numbers exist. And he proves that they are a lot. For instance, they grow at least like log x. Like they are at least below x, they're at least log x such highly composite. Okay, so these are some numbers that you can, looking at the patterns of the divisor sequence, you can come up with these numbers, and you want to count how many such numbers exist. Okay, so and he could give these lower bounds, and this lower bound is pretty almost kind of accurate up to some, the current answer, the right answer is, I think, some log to some constant. Okay, but yeah, so people nowadays don't study the sequence that much, like this sequence. But this sequence, the divisor sequence, is a sequence that people are really interested in. Even now, there is a lot of stuff about the divisor sequence, but that we still don't understand. Like, yeah, so there are hard open problems and really deep problems in number theory that will correspond to understanding some properties of this sequence. Okay, so this is one of the first papers that he produced while his time in Cambridge. And then there are other papers which studied these things called partitions. So partition of a number is just the number of ways to write the number as a sum of positive integers, right? So for instance, if you have 4, you can write 4 as 3 plus 1, or 2 plus 2, or 2 plus 1 plus 1, or 1 plus 1 plus 1. And so there are 5 ways to write 4 as sum of different numbers. So 5 is the so there are 5 partitions of 4. So you just write down, so this sequence, for every number, the number of partitions is called the partition number. So the partition sequence, the Pn, where you n looks like this: 1, 1, 2, 3, and so on. And the natural question is, how does this sequence? What do you know about this sequence? How does it grow? What properties do you know? Can you prove some arithmetic properties of this sequence? So Hardy and Ramanujan, so Ramanujan comes up and says that, oh, this partition number is basically like basically behaves like this crazy expression. So partition number of n is 1 over 4n square root 3 times e to the pi times square root 2n over 3. So this is an expression that really, like, mind blown. Like, even experts at that time haven't seen expressions like this, that some arithmetic function can behave like this asymptotically, and it was, and to more than this result, it's the technique of the result that's really important. The technique that was introduced to prove this result is called this circle method, and it's one of the most fundamental tools in analytic number theory, and it's my favorite, probably one of my favorite ideas. And it was introduced at that point by Hardy and Ramanujan to solve. Like, Ramanujan comes up with this, and then both of them write a paper together to actually prove everything rigorously. And it's yeah, so this method is for most fundamental tools in number theory today. So So I can sketch some ideas of how you prove something like that. What is the circle method? It's just that you can write down a series for this partition function. So imagine writing down a series. So just this formal series for the partition function, and and that series you can compute that it equals this expression, because so the way to see it is just that every partition, given every partition of a number, is basically telling how many ones exist, how many twos exist in that number, how many threes exist, and how many fours exist, and so on. So every partition corresponds to telling how many ones exist, how many twos exist, how many threes exist, and so on. And that combinatorial fact, when you write it analytically, corresponds to this expression here. And then then it's easy to see that this expression here corresponds to, so these are some geometric series. So you can explicitly compute that expression. So the expression, the generating function for this partition function is something explicit, and then we can compute. Okay. This just comes from basic definition of the partition function.
Can you just repeat this slide?
Oh yeah. So it's just that. Okay.
It is about partitions, right?
Yes, it's just partitions. I'm just saying the partition, you can write down a generating function for partition. Just from the definition, you can write down an expression for the partition generating function. Yeah. So it's just that. This infinite product will correspond. You can see that each term of this infinite product will correspond to a partition. So for instance, like if you collect 2, 4, and 8 here, that corresponds to plugging 2 1s, 2 2s, and 2 4s. So that will correspond to a partition. So each partition, and that will give you a partition of 1 plus 1 plus, this is 8, 12, and 12 plus 2, 14. So you can see that given any number, every partition comes up in this infinite product, and then we can compute that expression explicitly. So I'm being fast, but we can, if you have any questions, we can discuss it. Okay. So it's easy to just compute an expression for this partition function. That's something that people knew already much before. But then this real main innovative idea is that once you have that expression for P and Q to the n, you can actually write down an explicit formula for partition of a number n in terms of this series. Like if you know this series, you have, okay, for those of you who have seen some complex analysis, this is called the Cauchy formula, and it's the integral over a circle. So that's why it's called the circle method. So, right, this is a series which contains all the information about all the partition numbers, every number. But then if you want to figure out one number, you can write down an integral which captures that number. And then, so once you have the explicit formula, you have to analyze that formula. And to analyze that formula, typically, as you do in complex analysis, you have to analyze the singularities. The singularities occur at this roots of unity. And then somehow, so you have to analyze the behavior of this function, that this is an explicit function.
Faraday points are the same as Faraday numbers?
Yeah, so there's h over q, right? So this h over q in the numerator are just basically, yeah, rational numbers. Yeah, so and then this expression here has a lot of interesting, you have to really analyze this expression, we need to understand a lot more about that expression. For instance, the denominator of the expression is something that's well studied, and it has related to modular forms, and it has some modular transformations. Okay, so but anyway, so it just, you write down an explicit expression for the partition function's generating function. Then from that, you write down explicit formula for the partition number at a particular number. And then you analyze that expression using standard properties of the integral, like the expressions that you have. Okay, so this is a very high level overview of the proof. But yeah, if you are interested, you should look into it. We can talk about it later. But yeah, so this really introduced writing down this integral over a circle and then analyzing these arithmetic functions has been really important idea. Okay, so So later, that was about understanding what the size of Pn, at what rate Pn is going. And then, so that was a groundbreaking paper. Then he also actually studied some arithmetic properties. Like for instance, what are the, like he realized that partition number of 5k plus 4, numbers of this form is always divisible by 5. Partition number of the number 7k plus 5 is divisible by 7. Partition number of 11k plus 6 is divisible by 11, and so on. Okay, so these are some congruences he just has written down. The way he proves these congruences is just again using his style of manipulating series. So for instance, you can write an explicit from whatever I said before, just like a series for partition number, you can also write a series for partition numbers in this arithmetic progression, specific arithmetic progression. And then you can do really non-trivial manipulations of that series and prove that the series equals some infinite series like this. Okay, so once you have that, you can see that there is a 5 in here. Yeah, so that means 5 has to divide all, like you can see that this expression will 5 times something, some integer, give you 5 times some integer, like some polynomial with integer coefficients. So some infinite series with infinite coefficients. So 5 times some series. So that means each of the coefficients in the series is to be divisible by 5. So that proves his identity. That partition number at 5k plus 4 is divisible by 5. Okay. Similarly, even to prove other identities, he just writes down this infinite series, manipulates, and proves that, for instance, to show it for 7k plus 5, he derives some other explicit expression, the infinite series, and he sees there are 7s there, and 7 has to divide these numbers. Okay, so this is the style of Ramanujan proof. Now there are, these are partition numbers are some combinatorial entities. So now there are explicit proofs, but at that point, but there is merit in these infinite proofs. Like these infinite series and the manipulations are related to some fairly non-trivial mathematics. But now if you want, you can just prove them with some combinatorial proofs. And after Ramanujan, there are a lot of identities of these congruences that were proved. Even today, there are probably there are some congruences that people are trying to prove, search for, and so on about partition number. People write theses on these Ramanujan congruences. And the sort of congruences and the relations of partition numbers that Ramanujan studies are these what are now called Ramanujan identities. These are again relations between partitions. There's some some special partitions where parts differ by some size 2, and partitions where each parts are of the form 1 or 4 mod 5. So these are some special partitions, and he proves that these partitions, some P1n, and these other special partitions P2n are their equal in number. Okay, so you can, instead of just considering all the partitions, he's restricting to the kind of partitions that you're allowed to do. And then he proves that 2 ways of restrictions give you the same number. How does he prove these things again? Again, by series manipulations. He writes down a generating series for the first left side, and he writes a generating series to the right side, and through very non-trivial manipulations of the series, he proves that they're equal. So I mean, these are pretty non-trivial manipulations. I mean, if you, like for instance, I'll suggest, if you guys are interested, you should try to derive these things on your own. Like they are pretty non-trivial. Like it's like for instance, very first stuff were derived by Euler, and then yeah, it's not just something based. I mean, you can do it, but it's pretty non-trivial. It involves a lot of non-trivial manipulating manipulations. Okay, so these are these Ramanujan identities, again about partitions, proved using some Q series that Ramanujan really likes. But now this theory of Roger Ramanujan identities now belongs to something called infinite affine Lie algebras, some infinite dimensional Lie algebras. These are some objects that are studied in number theory, representation theory, physics, and so on. So, and somehow these identities show up in these studies. And people, there are things called vertex operators. People still study these identities of this stuff. Okay, so next important object that Ramanujan studied, again, it's another Q series, just like the Q series before. It's a series which looks like this: Q times 1 minus Q to the n to the 24. So this is an explicit series, and you expand it, you get some coefficients, right? So you have this Q series, it's given by this infinite product, and then you expand it out and you get this you'll get some coefficients. These coefficients are called the tau function of Ramanujan. So this is a series that he studied extensively, and he realized that these tau n's are multiplicative. So that means tau m times tau m n is tau mn. So the tau of 6 can be computed by just computing tau 2 times tau 3. Okay. Then he also observed that tau of higher prime powers can be written in terms of smaller prime powers. And he observed this bound that tau p at tau at primes seems to satisfy this bound 2 times p to the 11 over 2. And then
So
using
this particular problem was suggested to him, or he was himself?
No, I don't think it was. I don't think it was suggested to him. He was just studying them. Like,
so delta J's were not suggested by Hardy to work on, right?
I don't think so. Yeah. Like maybe I don't think Hardy really worked on modular forms. I think that much.
I see.
Yeah. So so these taus, so he observed these properties, but he didn't prove. This was an observation. But later these observations are really, really deep observations. They belong to the theory of modular forms. Like for instance, the multiplicative property is proved by model, and this introduced what are called Hecke operators in the very fundamental objects in number theory and modular forms. So to really understand this multiplicative, the basic properties of this function, the multiplicative properties, people had to introduce these Hecke operators into number theory. And then to understand this bound, which now is called Ramanujan bound, which is probably has influenced like so much in number theory. Like there's a field now when people study these things related bounds that people study. They're called Ramanujan conjectures. Like it influenced so many mathematicians, and like ultimately the proof of this particular bound is proved by Deligne using some very crazy tools from Riemann hypothesis of finite fields. So it had the proof ultimately came from some very high machinery involving Riemann hypothesis of finite fields. So it just the proofs are pretty hard, but imagine like he observed these facts and that he realized that these things are important, and they are really important. They are the backstone, like fundamental ideas of study in this subject called Langland's program, like number theory in general. So so this is probably like Ramanujan's one of the most deepest contributions to number theory, like in addition to like circle method and so on. Like for instance, for those of you who know what some modular forms are, the series that I've written down is what is called a holomorphic cusp form. It has weight 12 and level 1. What does it mean? It just, for those of you who don't know, what it means is that function that I've written down satisfies some nice functional relations. It satisfies these relations.
When that fourth formula was suggested by Ramanujan, LS equal to something, last slide.
Yeah, he has written down. I mean, this is just, you plug in this first two equations, you'll get this expression. Yes.
But idea and study of L functions was not in the fashion that time, right?
Yeah. I mean, it was not, people didn't think of it as L functions, just another series, like digital series or whatever.
Okay, yeah.
Now that belongs to study of L functions, and people realize there's a lot of arithmetic there, but at that point it was, it's some series that he was studying. Yeah.
So you have to say something about Weil conjectures. So this Deligne's work was related to Weil's conjecture.
Yeah,
right?
it's basically this. This proof came from Weil's conjectures. Yeah. So the Riemann hypothesis of finite field.
Okay.
yeah, it's yeah. So it's the fact that he could see it, and that's the fact that he realized. Sorry, realized it's important. Yeah, like it really requires tremendous insight that to see that some it's just a bound. Like for some people who are not used to analytic number theory might think, oh, how do some bound, just a bound, how much information can it have? But it like it really has a lot of information. Just it looks like in the sun bound, but there's a lot of information, geometry in it, and it proves a lot of things. Okay, so again, so the object of study, again, that delta is called it's a modular form, and nowadays people study these modular forms. These are fundamental objects in number theory. For instance, they were used in proofs of Fermat's last theorem. They're related to elliptic curves by modularity theorems and so on. This particular object is related to what is called the discriminant function of elliptic curves, and it's a very important object nowadays in number theory, geometry, physics, whatever subject you take. So okay, so some other I'm not going to, yeah, I'm going to rush it later. So yeah, some other crazy formula that Ramanujan realized was that this expression e to the pi times square root 163 is very, very, very close to an integer. Okay, so this is something Ramanujan realized, and this expression, for those of you who know some classical theory and so on, some arithmetic of these numbers of this form, it belongs to this theory of complex multiplication. And the reason that's true is because there's a formula which says there's this infinite series called the J function, and when you plug in some specific values, these values are called Heegner points. If you plug in these values, you get this expression here for plugging value for 163, you get an expression here and something very small. So so you plug in this Heegner point in the J function, you'll get an expression, and that expression will tell you that so this J value is an integer, and this is an integer, and this is very small, so this number has to be very close to the integer. Okay, so Ramanujan realized that, like, he was an expert in dealing with this complex multiplication. He understood. So I didn't have time to say much about elliptic functions. He understood elliptic functions a lot. Something called singular moduli and so on. Okay, so for people interested, they should look it up. This is a beautiful story, and it's still people study these specific numbers, how this J function and their fundamental objects in like different investigations. So these are some other expressions, and then another contribution from Ramanujan is just these formulas that he discovered using the same kind of techniques that he was like you see, you have this infinite series and some complex multiplication and so on. You substitute some values and you get specialized. So Ramanujan really liked special, like you have this, he has some general formulas, but he specialized those formulas to get expressions like this. So for instance, he got this expression for 1 over pi, and this expression for 1 over pi and related expressions are the fastest known converging sequences that help you to compute pi. Okay, so there is this whole machinery called Borwein integrals, Borwein stuff. Yeah, so like the standard expressions that you can imagine using trigonometric functions and so on are not they don't converge fast, but this expression here converges to pi, or here 1 over pi, really, really fast. So this also discovered by just manipulating infinite series and plugging in specific values. So in the context of this singular moduli. So this is something called modular equations. Okay. So yeah, so just like, I don't know, to even look at it as, even if you don't understand what it is, just look at it. That expression is really beautiful. Yeah. So
moduli means?
Yeah, this basically this 1 over square root. So these, because these points, the J at this points are integer values and so on. The J function at are in general algebraic integers. So those are called like in the
Is it something like singularity of the modular function, J function?
No. It just It's not singular in that sense. Yeah.
Okay. Okay.
They're special values. Yeah. Because they have integer values and so on. Okay. So then, like, there are other crazy expressions that he always dealt with. These integrals, he really loved different integrals. So these are some million transforms that he studied. He used to prove many integral formulae. He uses these definite integrals. Okay, so finally, let's see. So this was all happening while he was at Cambridge. He really was, but then he became sick. There's a story when Hardy goes and visits Ramanujan. Like, for instance, he visits Ramanujan at this Putney place, and like he rode in this taxi with number 1729, and apparently Hardy says, "Oh, number looks dull." And then Ramanujan responds, no, it's a very interesting number. It's the only number, it's the smallest number that can be written as sum of cubes of two numbers in two different ways. Okay, you can see that 1729 is 1 cube plus 12 cube. It's also 10 cube plus 9 cube. Okay, so this is a story that most of you might have been familiar with. But okay, so the reason Ramanujan knew this, like, it's not, he computed stuff like this before. The reason he knew this is because he was really studying this equation, x cube plus y cube equals z cube plus t cube. In general, if you divide by t cube, is also related to this equation z cube plus 1. But just by change of variables, it's related to this equation. So he was studying these equations, and he found even Fermat was interested in that equation. Euler was interested in this equation, but Euler found some general solutions to this equation, general rational solutions. Ramanujan also found some general rational solutions to the equations. Okay, so he knew the properties of these equations more in general terms. For instance, he realized that expressions like this, like there are two expressions of this form will, if you plug in that equation, will actually solve those equations. So you knew that these families, these are family, instead of one solution, these are an infinite family of solutions. So he knew that these solve these equations. Okay. And this equation is what is called the Fermat's cubic, and it's really well studied. And we know a lot about cubic surfaces in general. And Ramanujan was studying these parametric families. And if you specialize some values of m and n here, you'll get the things that we're talking about. Okay, so this is his paper. He has written down solutions. He has, like, for instance, he writes down, he has this crazy expressions written down, and he proves that once you, from that expressions like that, there's some infinite series, and those infinite series help you to each and every, all these terms kind of solve the same equation. Like, it's slightly different. There's a z cube was on the other side, but it's fine. So x cube plus y cube.
What was the last slide?
Sorry? Last slide?
What was the last slide?
Oh, the same thing.
Yeah.
This was the paper that
okay.
Ramanujan has. Like, he has written down this infinite series, and then he shows that somehow, okay, if you guys, this is quite easy to prove, but I don't know how one would come, like, I'm not sure how Ramanujan actually came up with it, but like, just you write down these rational functions and expand them out, and then you can see that the coefficients satisfy the equation that we want. Okay, so all of them lie. Okay, there's a +1, -1 business, but if you take n is even, but even values, it satisfies, they give you solutions to the equation. So all of them are about, like, so Ramanujan, it's not just, we often think of it as, oh, just he realized 1729, but he was really studying those numbers. Like, so for instance, in this paper, you can see that. I have a question
regarding this.
Yes.
So, have they found more examples of this nature? Because I've seen this paper by some Australian mathematician who explains this phenomenon. I think Haebel's, I forgot his name, starts with H. But what he does is he takes cubic plus cubic equals cubic plus cubic, where each of those terms within that cubic is a quadratic. It's a quadratic form.
Yes.
So what he does is he takes a quadratic form in such a quadratic cubic plus quadratic cubic in such a way that he just replaces x by minus x. And then one of the quadratics, he reduces it to Pell. And then the Pell substitution, when you put in, you actually get these solutions. And if you,
So that was the, sorry, I glossed over. So this, I think you get, so this, I guess this already is related to the Pell's equation. And like, so given some Pell substitutions, you can get some quadratic forms that solve.
Right.
Yeah. So
I was wondering if like more examples were created by that.
So people, I've actually checked it. Yeah. So people created more examples with starting from different, instead of these quadratic functions, some other quadratic functions and so on. Yes. Like, but I don't know what is the general theory. Like, I mean, there should be. Yeah. I don't know, but yeah, it's true that this whole study belongs to, people now realize it belongs to something study called, something's called K3 surfaces. So it's a pretty, like maybe, I don't think people are, for this particular problem, it's not like, I don't think there's a general theory, but yeah, there are generalizations.
I see. Okay. Thank you.
Yeah, thanks. So that's it. So I'll just try to wrap it up. So he returned to India, like, because he was really sick. And then this, like, finally he writes a paper, like, at some point about a letter to Hardy, saying that he discovered something called this mock theta functions, which are like, they are as beautiful as theta functions. So I don't have time to go into it. So they are what are called holomorphic parts of these things called mass forms, which are some very, very high generalizations of exponential function in some sense, like, which have crazy properties. And they're, for instance, recently they have been used, they appeared in study of quantum black holes and their entropy and so on. Okay, so so this is one of the mock theta function that Ramanujan studies. Finally, on April 26, 1920, at the age of 32, just 3 days after he made an entry into his notebook, Ramanujan died of sickness. So yeah, it's a huge tragedy to the mathematics community, and like in general, as a big tragedy that he's died so young, and one could imagine what he would have done if he had lived longer and like produced more mathematics. So his legacy, he has written on so many notebooks. People were studying a lot of his notebooks. For instance, after his death, like, there were research for some people like Bruce Burnt and like other people, like the research programs were based on like studying his notebooks and like proving theorems, generalizations of theorems, and making sense of, like, giving conceptual explanations of what Ramanujan has done, and like making sense of what some of the stuff that Ramanujan did. Like, for instance, this mock theta functions were not studied, like, something that Ramanujan studied at that time, were again have been studied quite recently, like in the last 20-30 years, they've been studied like quite extensively. So some of the things that Ramanujan, so legacy in like modern mathematics is obviously this Ramanujan conjectures, that the bounds I talked about, and the circle method. It's really important understanding equations and solutions to equations. And he has studied a lot of theta functions, and he introduced these mock modular forms and these identities that we have seen about partition functions, Roger-Ramanujan identities, and in even some subjects like combinatorics. There are these things called Ramanujan graphs. Ramanujan didn't study them, but they're named after him because they're related to these Ramanujan conjectures. And then these Diophantine equations and convergence to pi, and this 1729 is related to some very geometric, cubic surface and some K3 surfaces and so on. So these are some of the very few, like, top, like, main few like really important contributions of Ramanujan, and there are definitely much more. There's a lot to be like studied and understood. Just like he influenced a lot of like top mathematicians like Selberg, Sarnak. Everyone would study his papers and like they were influenced by his mathematics a lot. like, okay, so I finally want to talk about this one statement by Dyson. Dyson was a mathematician. He was at Institute of Advanced Study. He was a physicist, mathematician. So what he said, so whenever I'm angry or depressed, I pull down the collected papers of Ramanujan from the shelf and take a quiet stroll in Ramanujan's garden. I recommend this therapy to all of you who suffer from headaches or jangled nerves. And Ramanujan's papers are not only a good therapy for headaches, they're full of beautiful ideas, which may help you to do more interesting mathematics. So I guess I advise you guys to go and look at his notebooks and his papers and get inspired by some of his mathematics. Yeah, thank you. So let me know if you have any questions.
Could you please explain how we get the generating function for the partition?
Oh, yeah. Okay, so good. So I was rushing a bit there. So let's see. Maybe I'll do it here. Okay. Okay, so let's see. So I'm saying, so imagine that n is written in terms of some number of ones, some number of twos, some number of threes, and so on, right? Like every partition can be thought of as a certain number of ones here, there, certain number of twos, certain number of threes, and so on. Yeah, is that clear? So now, so q to the n would be, say if you have 2 ones, that will be q2 times 2. If you have 3 twos, it's q2 times let's say 6. And if you have 3 threes, it's q to the 9. Right? Is that clear? So if this was a partition, so then q to the n looks something like this. Okay. Yeah. So in general, so you give me any. So if you give me any such thing, so here is q cubed, maybe q to the 4, q let's say 4 and q to the 9, right? This will correspond to 4 ones, 2 twos, and 3 threes.
Yeah.
I think of it as 4 ones and 2 twos and 3 threes. So any expression of q to the n into these like this, you can expand out q to the n into these 3 things, for instance, where like you can think of each of such splitting of q to the n as a representing a partition. Yeah, that's fine. Okay, so now
that's fine.
Yeah, so now let's now just imagine that you're summing over all such expressions. So if you sum over all, like write down these expressions for q to the n for every q, all such splittings and all such n. So you first write down for all such splittings for a fixed n and then sum over all n. So what do you get on the left side? So q to the n occurs pn times. Is that fine? On the left, because you have pn, each number as pn partitions. So q to the n occurs pn times. Right? That's on the left side. But on the right side, you can see that you have all these expressions. And I'm saying those expressions can be thought of as just an expression of this form 1 plus. Okay, and so on. So this is an infinite product. Every term in this product, like for instance, this is 2 here, 4 here, and 9 here. So this product will give you terms. Those terms will exactly be all these terms that you see here. Right? Like imagine multiplying out all these terms. So you can see that like every term that occurs here will be here. Basically, is that clear? Like there are
that's clear.
And every term occurs uniquely here and so on. So that's why this p and q to the n is exactly equal to this expression. So the left side captures this partition q to the n, and right side exactly gives you, when you group together terms, you get a representation of a specific representation of a partition. that we have seen before. And that's why this is the infinite expression. And once you know the infinite expression, these are just geometric series.
Okay. Thank you.
Yeah. Okay, anything else? So yeah, I'll send you the slides or like references and so on. These are some references. So there are some great books if you are interested in Ramanujan's mathematics in general. Like Hardy himself wrote a book. I gave some 12 lectures on the subject, and there are a lot to learn. You can learn a lot from these letters. There's a commentary on letters of Ramanujan and shows a lot of mathematics of Ramanujan and so on. And then obviously you should look at collected papers and his notebooks. And yeah, like I guess Anirudh, he was asking, so this discusses some aspects of that
Exactly.
identity.
That's the name of the author, Michael Hirschhorn.
Yeah.
When I saw that, I remembered it.
Yeah. Okay.
Do you know of any
It
couple
just
of
2
references
pages.
which go in that direction? I mean, that is one thing that recently I started thinking about, as in creating more and more examples.
Examples were the same, like similar, like
similar style, like a rational function,
solutions to
quadratic by cubic, 3 such things, and then you expand them out, and you get just misses of Fermat cubic.
Okay. We can talk about it. Like just maybe
Okay.
at some point we can sit and talk. I'll see if I find some references. Yeah, we can talk about it.
As in, when I worked out, I could create like a few more examples. In fact, a family of examples, an infinite family. But what stopped me was I really wanted to create all kinds of examples which have that kind of structure, and that didn't go anywhere.
So it's not. It's not clear. Like in the sense, like from a high point of view, maybe there is some reason for why only certain families exist or something. We don't. Like we'll see. I mean, I don't. We can. Like I guess I can ask some expert in Diophantine equation.
Thank you so much.
Yeah. Okay. Anything else?
Yeah, thank you so much for such a passionate talk. Like, I'm sure the audience got to learn a lot.
Yeah, I mean, I guess I was rushing a bit, but hopefully